Hi and welcome to another maths video. I've seen this on Facebook and I wanted to show it to you. I've cropped out the name of the person who tried to answer a question like this because I wanted to spare them some embarrassment. But I do want to walk through this because there's some fairly common mistakes that can cost you dearly on an exam. And this might look complicated, so let's talk it through nice and simple. So first of all, this E and then this caret or circumflex or whatever x, that just means E raised to the power x, and E is just a number. It's roughly equal to 2.7. It's not a big deal. We don't need to care about what E actually means. And so the question is e to the power x plus e to the power 2x is equal to e to the power 3x. And we're basically trying to solve to find out what this is. Now a number of mistakes has happened here, so let's just walk through the reasoning and see what's gone wrong and how we might be able to fix it. So the first statement here, this is absolutely fine, nothing wrong with that, it's just a restatement of the question. For some reason the exact same thing has been done again. So again, there's nothing wrong with it, it's just an obsolete line because it's just a restatement of the question. So now this is where we run into our first problem. So what this person has done is to try to move this over the equals, which is quite right and it's a perfectly valid step. So the sign changes, so it becomes e to the power 3x, or negative e to the power 3x. So that's absolutely right. But then what happened to the equals? It's like the right-hand side of the equation has just disappeared. So don't forget that it is an equation and it does need to be balanced. So if we've effectively subtracted e to the power 3x from both sides of the equation, we're going to be ending up with 0 on this side. We still need to put equals 0 so we don't lose track of what it is we're doing. Okay, now here we have a huge mistake, huge mistake, and it's a very common one. So let's just quickly talk about the law of indices. A to the power b multiplied by a to the power c is equal to a to the power b plus c. And that is absolutely fine, that is correct. But these are not multiplications, this is an addition and subtraction. A to the power b plus a to the power c does not equal a to the power b plus c. You just can't do that because of this plus here. What we can do is factor though, but we don't know the values of b and c, so we don't know how many a's we can pull out. So even factorization would be rather difficult to say the least. So this step is an invalid step. So let's just quickly look at this, so see what we're doing. So let's say 2 to the power 3 times 2 to the power 4 is equal to 2 times 2 times 2 times, because we're multiplying here, times 2 times 2 times 2 times 2. That's 3 lots of 2 multiplied by 2 lots of 2. And look, they're all times. So that's equal to 2 to the power 7, which is the same as 2 to the power 3 plus 4. And that's how this law works. But if we try 2 to the power 3 plus 2 to the power 4, well, that's equal to 2 times 2 times 2 plus 2 times 2 times 2 times 2. And of course that is not equal to 2 to the power 7. Two times 2 times 2 is 8 plus 16, which is equal to 24. That's not equal to 2 to the power 7. Alright, so what we could do, I suppose, is to pull the 2 cubed out. And 3 times 2 cubed is not the same as 2 to the power 7. For one thing, there's a 3 here, which of course is not equal to 2 to the power 7. 2 to the power 7 is equal to 128. And 128 is not the same as 24. Okay, hopefully I've explained why that is wrong. Alright, so because that step is invalid, the other steps are going to be invalid. So this is now saying e to the power x plus 2x minus 3x is equal to e to the power 3x minus 3x. And that statement is correct. This statement is correct, but it is not equal to the statement above. These two statements are very different statements. It's a bit like saying the sky is blue, therefore my car is green. It makes no sense. This is what's known as a non sequitur. The one statement does not follow from the other. Okay, so this, now for some reason he's changed notation. He's gone from e to the power 0 to e as a function, so e has now become a function, so it's now e of 0 instead of e to the power 0, but he means the same thing clearly. We can tell that by context. So now he's saying e to the power 0 equals 1. And for some reason the equals has just turned up again magically. It disappeared here and here and here, and then it just reappeared. So e to the power 0 equals 1, and the natural log of 1 is indeed equal to 0, because any log of 1 is equal to 0, whatever base it is. So yeah, that's interesting what he's done there. I mean, these two statements do logically follow, but there's missed a step. So what he could have said is the natural log of e to the power 0 is equal to the natural log of 1. And then the natural log and the e comes out, so we get 0 equals natural log of 1. So that's how we got from here to here. Again, these statements are correct, but they have absolutely nothing to do with the question because of this invalid step here. Okay, so that's what went wrong. Now can we fix it? Okay, so what we have here, let's see what we can do. Let's let e to the power x equal u as a substitution variable. So u, whenever we see e to the power x, we're going to say u. So e to the power x is just u plus, now e to the power 2x is the same as e to the power x all squared. So e to the power 2x is equal to, let's give myself a bit more space, e to the power x multiplied by e to the power x, which is equal to e to the power x squared. But we know e to the power x is u, so that's equal to u squared. So that's u plus u squared. And then by the same reasoning, e to the power 3x just becomes u cubed, but let's go through the motions. E to the power 3x, we could actually say that's equal to e to the power x plus x plus x. And if we remember our law of indices, a to the power b multiplied by a to the power c is equal to a to the power b plus c. This is correct because we are multiplying. So this is equal to e to the power x multiplied by e to the power x multiplied by e to the power x. And when we multiply something by itself twice over, that's basically it cubed, e to the power x all cubed. But e to the power x is equal to u, so this is equal to u cubed. So that's how we get here. And we don't forget that all this is equal to 0. And now we've got a cubic equation. But this is actually quite simple because all these terms are u, so we can factor u out. So we have u into 1 plus u squared minus u cubed equals 0. So u equals 0 is a possible solution. In fact, let's investigate this before we go on any further. So e to the power x is u, and u is equal to 0. So can e to the power x equal 0? Is there any value of x that we can multiply a constant by to get 0? Well, the answer is no. Remember, e is a constant, it's not a variable, it's equal to 2.7 something, so 2.7 raised to the power of something will come to 0. No matter how many times you multiply 2.7 by itself, it's never going to come to 0. The only way to get it to 0 would be to multiply by 0, and 2.7 is not 0. So e to the power x equals 0 is not a solution. This is not possible. So we can forget the u as a possible solution. So u equals 0 is not a solution. So our only possible solution could lie here, where 1 plus u squared minus u cubed equals 0. Now this is a possibility. Let's just rearrange this just a little bit, and actually that is wrong. I've made a mistake here. That should not be squared because I've pulled the u out. So u divided by u squared divided by u is just u, and u cubed divided by u is u squared. So that was a mistake. So let's pretend I didn't make that mistake, eh? Anybody can make mistakes. And this is not u squared. This is just u. Which is why I wrote a 2 there where I shouldn't have done. What a silly Billy I am. Okay, and then that cubed should be a squared. Because I factored the u out, the u becomes a 1, the u squared becomes a u, and the u cubed becomes a u squared. Okay. So this is the only possibility where we might find a solution. Now, let's just rearrange this a little bit. Negative u squared plus u plus 1 equals 0. And I'm going to multiply everything through by negative 1. So that minus u squared becomes a u squared. Plus u becomes minus u, and plus 1 becomes minus 1. And that lot equals 0. Okay, so now we've got a simple quadratic equation. And if we have a quadratic equation in the form of ax squared plus bx plus c equals 0, well then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So u is equal to negative 1, but it's minus b or negative b, so it's negative 1, which would be a positive 1. Positive 1 plus or minus the square root of negative 1 squared. Well, negative 1 times negative 1 is positive 1, so that's just 1, minus 4 times a, which is 1, and 1 times 4 is 4, times c, which is negative 1, so 4 times negative 1 is negative 4. If you're subtracting a negative, it's a positive, so this becomes plus 4, and then all of that is divided by 2. And so what we have here is u equals 1 plus the square root of 5 over 2, or u equals 1 minus the square root of 5 over 2. Right, so the first thing is the square root of 5. Well, 2 times 2 is 4, so the square root of 4 is 2, and 2 is bigger than 1, so 1 minus the square root of 5 is negative, so in this case u is less than 0, which means u is negative. So e to the power x, remember e is just 2.7, it's just a number. It's never going to be negative because a positive times a positive times a positive is always going to be positive. So e to the power x cannot be less than 0. So we can eliminate this as a possible solution. So our only solution is e to the power x is equal to 1 plus root 5 over 2. And this is beyond GCSE, but there's something special about this number, 1 plus root 5 over 2. Save us having to write it out all the time. This is actually the golden ratio, which we call phi. So we can say e to the power x is equal to phi, which is the golden ratio, and then we can take the natural log of e to the power x, and that's equal to the natural log of the golden ratio, and then we can cancel and cancel, so x is equal to the natural log of the golden ratio. And that's all there is to it. So that's how we fix that problem. I hope that helps, and I hope that explains the issue, but the reason I wanted to make this video was to try to help you to avoid some of the simple mistakes that can cost you rather dearly in an exam. And even when you've got an intelligent person that knows about logs and exponents, these easy mistakes are so easy to make. And I'm going to leave my mistakes in to show you how easy it is to make mistakes, which is why it's important to double check your work and to check for any mistakes that you might have made. Okay, I hope that helped. Have a good day, and I'll see you in another video.